Okay, so now we're going to look at Newton's second law, and here it is. Okay, so Newton's second law states that the force is equal to mass times acceleration, and just as usual, force, and as I said in one of my earlier videos, force is measured in newtons, acceleration mass per second squared, and the mass is in kilograms. Okay, let's have a look. So I actually jumped the gun a little bit in one of my earlier videos, and I actually answered this question here. So what is the difference between mass and weight? So you can read through this and read that, and I explained a little bit more in the introductory video to forces. So you can go back through and have a look at that one. We'll just jump into the examples here. So example 1, what total force is required to accelerate a 1500 kilogram car from rest to 60 kilometers an hour in 6 seconds. So this is our mass, this is our initial velocity of 0, this is going to be our final velocity, and this is equal to time. So in our formula sheet, I just want to remind you of another equation. So we have F equals ma, but we also have F is equal to mass times v minus u, so the final velocity minus the initial velocity over time. And all that is doing is substituting our equation for motion for acceleration into the force equals ma equation. Just remembering that we need to convert 60 kilometers an hour into meters a second. So v is equal to 60 over 3.6, which is equal to 16.667 meters per second. And the more decimal places you go to, the more accurate it is going to be. Alright, so now we have this, we can actually just put everything else into our equation. So force is equal to 1500 times by 16.667 minus 0 all over 6. And that is equal to 4,100, I don't like that, 4,170 newtons, and that's the 3 significant figures. Just to remind you, in the course we can just go 3 significant figures, and then that's acceptable in an exam situation. Okay, so what is the weight of a person of mass 60 kilograms on the Earth? Acceleration due to gravity is 9.8. I'm going to put in a little 1. That's meters per second. Okay, so just remembering that weight is a force, and sometimes we call it we put a little subscript of W in there. Might do that now. So we've got the weight force is equal to mass times gravity, which is equal to 60 times 9.81, which is equal to 589 newtons. Okay, so here I'll just make an F there instead. So the force of gravity, or the weight force on the moon, is going to be, again, so mass doesn't change, so that's going to be 60 times 1.6. Then that one is equal to 96.0 newtons. So just like I said up here, we're going to 3 significant figures. This is, so when we put that decimal place in, that signifies that that's a significant figure as well. So I've gone to 3 significant figures there. Technically speaking, we probably should have only gone to a 2 if you go through significant figures, because we've only got 2 significant figures here. The maximum we should have, because it's times, is 2. But you won't be deducted points in this course if you are if you go to 3 significant figures. Okay, so the last one here, same thing again. So force is equal to 60 kilograms times by 23 meters per second squared, which is going to be equal to 1,380 newtons. Okay, and if you look at these 2 accelerations, the acceleration due to gravity on Jupiter is about twice as much as the acceleration due to gravity on Earth, and as we can see from our calculations, it's roughly twice as much as well. The force is as well, because they're proportional. So you can always kind of check your answers that way. Okay, so example 3 now. Okay, so these are some discussion problems. So explain the following in terms of Newton's first law. You are sitting in a car which brakes decelerates suddenly, you feel yourself being thrown forwards within the car. Okay, so Newton's first law, N1, an object will continue in its original motion unless acted upon by an unbalanced net force. Okay, so as the person wants to keep on going, so the person in the car, therefore the person in the car will continue forwards until acted upon by a seatbelt. Hopefully you're wearing your seatbelts. You don't want to be stopped by the windscreen. Okay, or worse. Okay, so you're thrown forwards in the car because the car suddenly stops, but the body inside it wants to keep on going in its original motion. Alright, part B, you are in a car going around a sharp corner. You feel yourself thrown outwards within the car. Okay, so if we look at our car, try and draw a car. This is not very good. I don't know what kind of car this is. Maybe a station wagon or something. Got the roof. Not too bad. Okay, so it's going around a sharp corner like that. And if this car was just to go to want to, like, in its original motion, if we see this original motion is just straight ahead. So everything within the car, its original motion will be straight ahead also. And then again, just like the first problem, the seatbelt is what's connecting us to our car, the seatbelt of the seat. So you will be thrown like outwards, but really you'll just be thrown in the original straight line that you're going in. So you're going in your car around a sharp corner, you feel yourself being thrown outwards within the car. So again, you could just say, you could write a similar answer to part 1, part A. For that one. Just a quick note, if you're in an exam or a test and you're stuck and you think, oh, how am I going to explain this particular one in terms of Newton's law? Just stating the law is a really good start. So if you can remember Newton's first, second and third laws once we've done them all, just state them. If in doubt, just state them, get something on the page. You might get some marks for that, and then try and make it relevant to the actual question. Okay, example 4. Okay, explain the following in terms of Newton's first law. An astronaut in orbit around the Earth feels weightless. Okay, so basically when you feel weightless, our net force is equal to 0, which equals to mass times gravity. So therefore the gravitational acceleration would be equal to 0. And so this happens when all the forces acting on the astronaut are balanced. And then they feel weightless. So I looked up an article on this in the Scientific American, and the astronaut that they interviewed in that one said the best comparison you can have on Earth is actually floating in water. So being weightless is kind of like floating in water without the sensation of the water actually on your skin. So you can think about that next time you go for a swim. Think about the astronauts in space. Okay, a person in a rocket or a lift accelerates upwards, feeling heavier. Okay, so let's imagine that we've put a person on the scales. They're standing on one leg there, but they're about to stand on the 2, I think. So these are our scales. Think about the forces acting on this person. So we've got our force due to gravity. So it's mass times gravity. And then we have the normal force here. Okay, so when we're just at rest, the forces, mass times acceleration, are equal to 0, and therefore n is equal to mg. They have to be totally balanced. So they're balanced, the person's not moving, the scales aren't moving. Now let's put them in an elevator. So let's put this person again. And their scales. Let's put them inside an elevator. Those scales should be connected to the floor. That's funny, but anyway. Let's make the floor large. Okay. So we have still our force due to gravity. And we still have our normal force. But this time we also have an acceleration, A, going upwards as well. So acceleration is going upwards. So if we think about our forces, so remember that the net force, so this is like the net force, is equal to mass times acceleration. And remember when I was explaining the forces, the net force is equal to the sum of all forces. So let's say that upwards is positive. Let's say that's positive, upwards. So that means that the normal force is positive and the gravitational forces are negative, and they're equal to ma. So let's now add the force of gravity to both sides. So we're left with ma plus mg is equal to the normal force. Right? And so then mass is equal to a plus g, which is equal to m. So the normal force is what the scales actually measures. The normal force is what it measures. And so what this will look like on the scales, it'll look like your mass is actually larger. So a person in a rocket will lift, which accelerates upwards, feels heavier. And that's because the scales are measuring both the acceleration due to gravity, but then also this acceleration upwards, because you're not going up or down through the air. So your normal force still has to be balanced. So there's more force going through the floor, essentially, than normal. Okay.